Steve, how you doing?
I'm doing all right, man. Thanks for coming by.
I kind of hurt my knuckles a little bit.
I'm sorry about that. But welcome to Device Squad, the podcast for the mobile enterprise from Propelics. This is a very special night. Normally, I do the podcast over Zoom, but tonight I have with me John Hershey in the same room. We're sitting just a couple of feet apart from each other. There's a full moon, and it's like 50 degrees out in the middle of January in Massachusetts. Tonight's episode is going to get a little futuristic. Or maybe not. I don't know. Maybe all this technology is already happening somewhere in an underground lab at MIT.
Sure, it's presentistic.
At the very least, it's already happening in the mind of John Hershey, who joins us today on Device Squad. Device Squad, fighting crimes against enterprise mobility worldwide. Bad UI, frustrating user experiences, poorly conceived mobile strategies, we defeat them all. This podcast series will cover all aspects of enterprise mobility, including strategy, development, design, testing, and more. My name is Steve Brickman. I'm a mobile strategist and UX architect with Propelics. First, a brief history of the company. Founded in 2011, Propelics is a mobile strategy consultancy helping enterprises worldwide devise true mobile strategies and develop world-class mobile applications across all industry verticals. Propelics clients include large companies like Amway, Bright Horizons, Bank of Montreal, Dubai Airports, Family Dollar, DLL, Cintas, Merck, and many more. Propelics' menu of services includes 8 different mobile kickstarts, covering everything from mobile strategy and road mapping to MCOE to UI UX design to mobile testing strategy, along with soup to nuts app design development and support. Additionally, Propelics offers 3 homegrown enterprise mobile products. Aside from being a good friend of mine and from just living a couple miles down the road, John is a senior principal research scientist at MERL in Cambridge, where he heads the speech and audio team since joining MERL in 2010. Before that, John spent 5 years at IBM's T.J. Watson Research Center in New York, where he led a team in noise-robust speech recognition.
That I did.
He also spent a year as a visiting researcher in the speech group at Microsoft Research after obtaining his PhD from UCSD in the area of multi-modal machine perception. He is currently working on deep learning for signal separation, speech recognition, language processing, multi-modal semantic representation learning. So usually I know something about what my guests are talking about, but tonight I can honestly say that I know nothing about any of this stuff. It's so fascinating, though, this stuff, because we're getting into an age of widely available products that specialize in voice recognition, like the Alexa and so forth, Amazon and Google's device. We just got an Alexa, and we've been using it for Spotify. We use it like every day, though, because we're constantly listening to music, and we're sort of equally frustrated by it and delighted by it, I would say. Because we're delighted because it can't understand Sadie yet. She's our 3-year-old. So that's good.
That's built-in feature, I think. You can turn that off.
She says, like, Alexa. She can't get the X. She doesn't have X yet. So it can't figure that out. It's like, I don't know what you're saying. But we're frustrated because it easily understands what Gus is saying. And he's our 8-year-old.
So he just orders stuff.
So it's constant Minecraft songs. I didn't even know there were so many songs about Minecraft. But anyway, the reason I bring it up is because what I've noticed is that each member of the family has a different style of interacting with Alexa. You know, I'm the technology guy, so I just sort of say as concisely as possible. I just say, Alexa, play Come Together by the Beatles.
Right. Robotically almost.
Yeah.
And even maybe like putting a little pause between the words, like
right, to try to give it a little break.
segmentation.
Yeah,
humans can learn too.
Gus, he will say, "Alexa, SpongeBob theme, SpongeBob SquarePants." That's a direct quote. He'll remove the verb altogether. Somehow he already figured out that the verb is unnecessary.
Because of Googling, right? It's like you're just searching for keywords.
Right. Reagan, my wife, on the other hand, she is from the Midwest. She's from Chicago. So she has that disease where you have to be nice to people all the time that they have out there in the Midwest.
Yeah. Kind of creepy.
So Reagan will say, "Alexa, could you please play Lost in My Mind by Head in the Heart?" She may not say please. I may have just thrown that in. But she does phrase it as a question. She'll say, "Can you play blah, blah, blah?" And I say, "Reagan, you don't have to ask it."
Especially a yes or no question like that.
Sadie is just frightened of it. She's just scared by the whole thing. I think maybe because it doesn't understand her. There's a disconnect. So she runs screaming. So, who had it right in the family?
Well, if it worked, it was right. I kind of like Gus's approach. I mean, search terms, you really just get rid of, all the techniques try to minimize the impact of those other words that don't really matter.
There's like slightly less processing time required without the verb.
Well, they're noise. All those little tiny connecting words are just noise. So, well, who's does it work the best for?
Probably Gus.
I was thinking you, right? No?
Well, it actually misses a lot. For some reason, it's very buggy. We'll ask it to play a song, and it'll say, "I can't find it on Spotify," but we know it's on Spotify because it played it yesterday on Spotify.
Lying. That's not a miss.
That's a bad character trait for Alexa.
It's very human.
Now I'm a little nervous. Now that I know that she's not to be trusted.
Well, she is taking all of your household data.
Is that what, like, just all
conversations?
Yeah, that's okay.
Is that true? Actually, haven't actually read the manual on
I haven't either. It may very well be true.
I checked into the Koji robot. It's a little toy robot that has personality.
Yeah.
And I thought, this is the way if you wanted to train, an army of robots, you would just sell them as toys and have them practice out in the field, get the data and then dump it into your network thing.
I think I learned something about you tonight that I was not aware of.
But no,
I was an evil genius.
I was Christmas shopping.
Okay.
For my kids, and I thought about getting that.
A toy to take over.
And then I thought maybe it would be recording all the data. But it doesn't. I looked at the manual. It only sends like parameters or something.
Oh, the robot.
This was the Koji robot.
Koji.
Personality driven.
Well, the Alexa, you're supposed to say Alexa.
And she does have that little blue eye or...
And then it lights up.
LED thing.
Yeah.
That spins around and looks at you. But she's kind of creepy.
It's kind of creepy.
She doesn't have a lot of visual personality.
No. So that's a question. Are these objects constantly listening for Alexa, obviously, right? So it's...
Yeah, it has to be listening for that. And,
yeah.
It's a matter of policy whether they record everything, but I don't think you can be successful in one of these games unless you do record the data and use it to train the system to be better. So
sometimes it will just start talking, and we have not asked it to talk. Whether it was a word that sounded like Alexa, it mistook for Alexa, or whether it's just making an announcement, because it does that too now. It just spits commercials out now.
She'll just cut you off, right? She won't sort of like ease into it, like I just did. Like I kind of interrupted you, but delicately. Yeah. But she'll just cut you right off.
It's there. It's just...
You're just like, hey, I don't know, I was going to say what I'm going to say, and you're going to order...
Right. Yeah. She's got some...
Like can of hearts.
Because we're in the middle of a conversation. It's not like a quiet room. I think the few times that it had happened that we've been in the middle of a conversation and just like, oh, Alexa's talking to us. And
right, so she's got serious neurological problems.
So they may want to work on that. That's part of the programming, to say, don't throw an ad out there unless it's quiet in the room. Although maybe if it's quiet in the room, then nobody's there. So why would you say it?
Yeah, just think about what you're saying and doing before you do it. I think that's the main lesson.
I wonder if it could even wait for keywords that are related to... Well, now you're getting into the marketing angle.
Now, I mean, that kind of stuff has gone on
That's
quite a
going
bit.
on.
The always listening kind of interface that is then going to recommend things.
Boy, where should we go eat tonight, honey? And then for Denny's.
There's a restaurant nearby.
That's interesting. I mean, this idea that eventually these products will just service us automatically.
I was thinking about that today. Like I was followed somebody into their office, and it was dark, and he started to move his hand towards the light switch, and I was there, so I just flipped it on, and I was like, hey, well, wouldn't it be great to have a robot that just anticipates what you need to do? Because the people around me are not doing this. You know, I reach my hand out, and like nobody puts a beer in it or anything. Why couldn't a robot do that? They don't have anything to lose.
Anticipate everything, and then gather data based on the local environment in the room.
Be a little helper.
And also the time of day, past usage, all these things can become trainable so that, it's Friday and it's 7 p.m. and, the machine asks, are you guys going out? Where are you going? It almost just becomes like another person in the room.
Yeah.
Like who's just wants to help all the time.
It's a personal assistant. I mean, that's all of these guys from Siri to Alexa. They're personal assistants. They just don't have bodies, so they can't do squat. But when they're driving drones over with the things that you didn't realize you wanted until they arrived at the door, and then you couldn't resist.
Emotional states are already being recognized, right?
Yeah,
by
for sure.
Artificial neural network.
Actually, I did my grad school career in a lab that was looking at emotion recognition. So my advisor was Javier Mobian. He's now at Apple. He made a startup to recognize emotion visually, and they were acquired by Apple, so he works at Apple now. It's a very important and big area now to try to recognize emotions because it tells a lot about humans, right? What their emotional state is.
Especially in terms of trying to interact with humans. So if we can assume that AI systems will easily identify our emotional states, how long before companies start marketing towards our perceived emotional states? So it'll say like, oh, you seem a little depressed today, Steve. Maybe you'd like to watch a comedy.
Yeah.
I'm just wondering how long before that happens. That seems very close to me. It's just a piece of the larger picture.
Just pulling you in.
Yeah, it's just part of what time of day is it? What have they done in the past? Yeah. What are they talking about in the home? And what is the general emotional state that I'm sensing?
I just saw the future of all of this. So you know how like when Disney makes a movie, they have these like emotional stages of plot?
Yeah.
It's like connect the dots, right? They've got a formula.
Right.
Couple of ups and downs.
Yeah.
Right. So that's how they pull you in. Like you want to watch the rest of it. And now previews, I just went to the movie theater the other day and the previews just looked like a movie. There was no narrator.
Right.
It was just a long extended clip that was pretty connected of the movie.
Yeah.
They're just trying to pull you in, right? Maybe that's what it is. Like, get your emotions going, pull you in.
Maybe you could even program that in. How annoying do you want Alexa to be?
Yeah.
How intrusive do you want her to be in your life?
How much comedy, how much drama?
Yeah.
You know?
Do you want her to be funny?
Histrionic? Or whatever the opposite of that is.
Interesting. So while our emotional states are being watched, we'll also be able to control the personality of the actual AI.
Or it will be controlling us.
Or it will be controlling us. Thanks, John.
There's a whole future in reading your mind, I think.
The funny thing that happened the other day was that I've heard about this deal that they had on Amazon for a coffee maker. And it was an Alexa deal. This is what they're doing now, too. It does good coffee maker. It's very high-end. It's got the grinder built in. Anyway.
The coffee that speaks to you.
They're obviously testing out spoken e-commerce. So, I'll try it out. But Reagan was just in the next room, so I had to whisper it because the deal was running out. So I had to do it if I was going to do it because it was like $40 off. It was good savings. But I didn't want her to hear it because it was a surprise. I was going to make it a surprise Christmas gift, so I get the Christmas gift out of the way at the same time that I do. I could probably write it off, right? Because now it's research. Anyway, my point is I had to literally lean down. It became a very intimate thing. I leaned down to the Alexa dot.
Alexa could feel the steam of your breath.
And then I said,
array.
And I said, Alexa, order a coffee maker. Which is what you have to say. The funny thing was that once I requested it, I thought this is really slick. But Alexa's hooked up to our stereo for Spotify. And so she repeated it back. And it reverberated through the whole house. So these are new issues.
You're like, no. There's no Alexa again. She's always just shooting her mouth off.
Shooting her mouth off, ordering coffee makers. Did you hear me order a coffee maker? I don't think so.
Exactly.
Yeah. So these are new issues, new privacy issues.
Well, polite machines, I think, is an interesting new issue. We don't have those yet.
If I'm whispering to you, you should whisper back to me.
Duh, yeah.
And that's not
part
built
of
in.
the social contract.
Yeah.
They don't have a social contract.
That's a big problem.
Big problem.
Big problem.
Meet your new friend who has no social contract.
That's right. And no legal obligation not to record everything you're saying.
And can't think at all.
Yeah. So, okay, let's brighten this up a little bit. So, you recently got back from a number of tech conferences. You do a lot of traveling.
Yeah.
And I apologize for giving you an antique chair. So, you were at NIPS, Neural Information Processing in Barcelona.
Yeah.
And then you were at San Diego at the Spoken Language Technology Workshop. And then you were at an Uber party. I think I'm most jealous about that.
That was in Barcelona.
Oh, that was in Barcelona. To celebrate the launch of their AI lab. Tell us about the NIPS.
Yeah, so NIPS is it's a machine learning conference. I don't know how much you're aware of the history of machine learning and deep networks and all that stuff, but it's been a very up and down kind of roller coaster ride over the decades. And now it's in a huge upswing. The machine learning work that's going on now is breaking records all over the place,
Why do you think it's sort of coming into its heyday now? Is it just because the processors are there, or it's affordable now, or?
It's absolutely the processors are there and the right methods were finally realized to work, given the amount of computing power. What's working now is basic technology has been around since the 80s. And in between, we went into all sorts of more sophisticated things because they had better principles, we thought, or they had better computational properties or something. But it just turned out that what had gone on in the 80s was actually the answer, and we just didn't scale it up.
Wow.
Yeah. Neural networks.
The neural networks.
The neural networks. They very popular in the 80s and early 90s. And then at NIPS, every year they would make a little model of what words best correlated with your paper being accepted to the conference. So maybe 20% get accepted.
Yeah.
And which ones were worst words to have in your paper. And neural network was about the worst thing you could write in a paper in 1990. I mean, it was just immediate rejection, basically.
Wow.
Yeah, and now it's like everything is deep network.
So how do neural networks work? What are neural networks?
Like I said, they've been around for a long time, and they were one of the leading computational theories for computers way, way back in the day. If you think about the origins of computer science with von Neumann and Wiener, they were interested in both the classical symbolic paradigm as well as this kind of floating point kind of thing, real valued computation. Analog, right? Digital and analog. Digital won out for computers because it was easy to write a program symbolically. But that paradigm of adjusting some parameters and learning a complicated analog function was thought to be more like the brain. And computers famously failed at doing the things that people were able to do.
So when you say learning an analog function, we just break it down a little more.
Yeah, sorry.
So digital ones and zeros.
Digitals are ones and zeros, yeah.
And when you say analog, how is that processed? How does that work?
We don't implement it in an analog computer. It's just an analog model. So when we think about writing a program for a computer, it's a bunch of letters, each one which is a discrete symbol, right? And they make up discrete words, and there's a syntax and grammar for this symbol set that allows you to define a distinct procedure that proceeds from one state to another and stores variables in memory and so on, right? But an analog computer, the idea is that the representation of the state is not a discrete set of truth values or specific states in terms of a sequence of operations. It's more like the state is represented as a big vector of numbers, big array of numbers that are continuous. And you transform the state of the system from one state to another through this big nonlinear function. And this is how the brain was thought to work. You have neurons that receive a bunch of signals and maybe calculate some correlation between them. And then when the right pattern of inputs arrives, they fire a new impulse, which propagates down the neuron and goes to the next set of neurons. And so there's this interconnected web of neural axons and dendrites, branches that connect the neurons together. That's how the brain works. And so, since the human brain seems to do something useful from time to time, they thought that they should mimic that. And so the whole history of neural networks basically comes from trying to do what the brain does.
So neural network, is that necessarily a network of machines?
I mean, we use it in the term in different senses, but for the purpose of machine learning, the neural network is a machine learning model that is loosely based on neurons, on the concept and connectivity, that you have a set of inputs and that the computation that needs to be done can be represented as taking those inputs and multiplying them by different sets of numbers, continuous multiplication of these numbers, and then passing them through some other functions like gating functions and things like that. So, the two things, the classical computer architecture and neural network architecture, can overlap. There's sort of a continuum between them, because the nonlinear function that the neural network uses, if that became a gate, like a discrete gate, that says, I'm going to have one value if you're below a certain level. Like say if the number that comes in is below 0, you have one value of 0, and if it passes 0, then you go to the value of 1, right? Then it's a logic gate, and you can build a conventional computer out of those discrete logic gates. But the idea is that with a neural network, you can do this sort of nuanced computation that we think perception must be based on. Because in perception, there's not an exact answer for every question. It's kind of a matter of gradation. It's a matter of combination of many attributes, and those things can be combined with different strengths. So it's more of a continuous model rather than like a logic model.
But your specific focus is around audio recognition, signal isolation.
Yeah, so I started off being interested in music, and I was trying to understand why we have harmony and things like that. And it turned out that the only way that in my little private theoretical world, that I could explain harmony was by means of asking the question, what's the primary purpose of hearing? Think about, evolutionarily speaking, we evolved to hear in order to recognize different things. But in order to recognize things, we have to separate them, because in the jungle, all the sounds are overlapping, and you need to be able to detect very subtle sound, even if there's if the waterfall is there and the jaguar is creeping up on you, you need to be able to hear that. So separating one sound from another is kind of a primary function of hearing.
Right, sure. Huge advantage to be able to do that.
But so what does that have to do with music? Well, music is all about harmonies and disharmonies, and it turns out that our ability to sort of recognize separate notes and track different objects in general, different auditory objects, has to do with the pattern of their harmonics in our ear. And those harmonics, because they're have these mathematical relationships, this harmonic series, they overlap in different ways when things are in a classical sort of harmony with each other. And that, because of the way the ear is constructed, because of the physics of it, it causes different vibrations. So everybody knows about beating sounds, or musicians at least know about, when two notes are out of tune with each other, they make a beating sound. And so piano tuners listen to the beats. But what happens when you have a dissonant note is that the beats are at different beating rates in different parts of the spectrum. My idea was this causes dissonance because that is a cue to separate those different little fragments of sound as if they were different sounds.
Mm-hmm.
Because one of the big ways that we separate things is that when they have different modulation patterns, then they tend to come from different sources. I started from music, and I was doing audiovisual perception in school when I was doing my PhD. And I also worked on audiovisual pattern recognition, where you want to tell where a sound is coming from by watching, seeing what movement is correlated with the sound, things like that. Then I started working on separation of one sound from another.
So that the robots can attack us with more efficient aplomb.
Precisely. When you step on a twig, sneaking away from the robot,
it'll know.
It'll just wheel around.
And it'll be able to isolate that twig noise from all the other background stuff. And thankfully, you had the legions of toy robots that you were able to develop the software on. I think I'm on to you now.
Yes.
I'm going to lock the door.
There is an anime character called Naruto.
Mm-hmm.
And Naruto's mad skill is that he can go and replicate himself 1,000,000 times and then practice like a particular judo move or something and then unreplicate, and then he's like an expert in 5 minutes.
Mm-hmm.
And so this is how the robots are going to start getting an edge, right? Because if you have 1,000,000 robots out there, even if each one would learn 100 times slower than a human, the whole thing is going to be learning 10,000 times faster than a human, because humans can't transmit their experiences, telepathically to each other, and their learning is completely isolated to one person. But a robot can share everything.
So how much time do we have left then before the robots just completely take over?
Probably about 10 minutes.
10 minutes from now.
Nobody has rolled out that army of toy robots yet.
It's funny that you would go that route, because I've actually noticed that as a real thing that happens. I think I was reading about reading brain waves to control tools and how doable that was. And then the next thing I know, Mattel has
have a brain.
A toy.
An EEG toy.
And I saw it at the swap shop. Yeah, I'm not even joking. You put it on your head.
I'm ordering it right now.
And you just think about moving it. I'm sure it's extremely limited and hardly works at all. But the fact is that they thought they could do it. They thought that they should turn it into a toy. So what you're saying doesn't seem too far off from reality. So, you and I were both impressed with Google's Deep Dream. And maybe some of you out there know what that is. You take a photo and you run it through a processor.
Oh, it's amazing, yeah.
But is it still amazing?
Has it stopped blowing you away?
Stop blowing me away. Because
Yeah,
at this point, I'm just assuming that it turns everything into dogs or eyeballs.
They really
what
have
I've
a
noticed.
problem with the dogs and eyeballs.
So my question is, aren't they just telling it to look for dogs? I mean, what is it doing? Really, Deep Dreams, isn't it just looking for patterns in images, and then it's just turning those patterns into dogs? Isn't that really all it's doing?
The objective of it? Is that what you think that was what it tried to do? No. It was an attempt to understand how the neural network works. So, one of the big things in vision was the invention of the convolutional network, which happened decades ago. Convolutional neural networks were reinvented to scan the whole image and recognize everything in the image at every place. So it's like the same network as if you duplicated it at every pixel all over the whole image. So it's trying to process all of the pixels in the same way, and then it comes up with a classification at the other end. Okay, and what they do is they emphasize what was recognized by manipulating the input until it increases the recognition of whatever was there.
Right. Extrapolates.
It extrapolates, it accentuates, it's like a feedback loop. If something is recognized, whatever was more likely than less likely, they increase.
Yeah.
They want to increase the recognition of that thing, so they optimize the input to do that.
So it's kind of like a simulation of imagination.
Well, I wouldn't say that. I mean, what I would say is that it was a way of trying to understand how the network works. What you can learn from that, you look at these things, and a local patch looks like a piece of a dog or something, right? But if you zoom out, it's like a dog with 11 heads, Yeah. And it's like a weird, unrealistic global image when you zoom out. And that's because there are no long-range dependencies in the network. And the reason for that is that those images don't occur in reality. So the network never has to distinguish between an 11-headed dog and a one-headed dog. All dogs have one head. If it can recognize any part of that dog head, there's a dog there. It doesn't have to distinguish between real images and bizarre images that have all of the features of real images and more. So what was interesting at NIPS when I went to Barcelona this December is that there's a paradigm in deep learning that's kind of hot right now called adversarial learning. This is used to generate realistic images that are globally realistic. You don't get dogs with 11 heads. The reason is you have one network trained to distinguish those like a real image from whatever you're generating, and it's in competition with the network that's generating the image.
I see.
There's a completely different approach, and it generates much more realistic things.
So here's what I don't get. When we talk about some of these things, we talk about this network examining this image as though it were looking at the image. But it's not looking at the image, right? I mean, if you look at like a JPEG image, it's just a series of numbers, right? It's just this pixel at this location has this RGB code, right? It's just, everything is just a bunch of numbers that reflect how it's going to be presented on the screen. So is it really ultimately just looking at a pattern of numbers? Or like that's...
Yeah, I mean, that's you're way ahead of most people, because the usual response that, someone who does computer vision research gets from like a student would be, why is it so hard? All I have to do is move my head around and I see things. You just look and the image goes right into your brain. I mean, why is that so difficult? And it's not until you think of it as a big array of numbers that have to be processed that you realize how hard this conceptually is. And now we have methods where, any high school student could download the tools and start training a deep network. And, that can do amazing things, but they won't understand how it works. And that's the mind-boggling part, is like, it is just a set of numbers, one number for each pixel, or three numbers for each pixel. You've got RGB, you've got three numbers. How are you converting that into the recognition of the dog? And it's just a cascade of simple transformations, each of which is very simple and doesn't do very much. But because it's a deep network, there are many layers of transformations, and they're all trained to achieve that recognition. There's a compounding effect of all of that.
So it would be the same for audio recognition, right? I mean, it's just the audio is being recorded and it's being converted to numbers.
Yes.
And then it's just translating these billions of numbers into meaning.
Yeah. So the thing that's interesting is, how has that changed over time? What did we used to do before the deep neural networks? Let me just run through a model so you get a better idea of what it actually is. So you have a set of values called features, right? RGB codes for your image, or you might have like the energy in each frequency for sound. Okay. And the way that those get transformed in a network is you take that series of numbers and you multiply it by a matrix. What does that mean? It means that over and over again, we take each of those numbers and we multiply it by something. Then we take the next number, multiply it by something else, and we add that whole set of products up. And we do that in like 100 different ways. Just keep doing that. And for each of those big sums of products, then we run that through another function. For example, the function is like a function that starts out at 0 and then ramps up to 1. And then it stays 1. So it's like a smooth step function. Mm-hmm. So you can think of that as making a decision, right? Am I on this side? Am I on that side? Or am I somewhere in the gray zone? And that gray zone is what distinguishes neural networks from like a logic system. It's because of that zone of uncertainty that we can actually like optimize this thing gradually. If you had to tune a bunch of decision points in a kind of like a discrete symbolic system, you'd have to try every combination of things. It would be impossible. So when it's smooth, you can do something gradually and ultimately do learning.
Let's just talk about this Universe project. A software platform for measuring and training an AI's general intelligence across the world's supply of games, websites, and other applications. Universe allows an AI agent to use a computer like a human does by looking at screen pixels and operating a virtual keyboard and mouse. We must train AI systems on the full range of tasks we expect them to solve, and Universe lets us train a single agent on any task a human can complete with a computer. So they're basically putting robots into these environments, and they're having them learn about our world by playing in video game worlds.
I would say that's a very optimistic characterization. So, like, if you think that your, like, teenage son, he's 18 years old and he's sitting down there playing video games all the time, if you think he's going to be learning about the real world, you got another thing coming, right? They're not learning about the real world, but they're learning about a world that's small enough that they can learn. These things are doing amazing things, but it's still peanuts compared to operating in reality.
So they're putting these robots in Minecraft to learn about three-dimensionality of the real world.
Yeah, it's totally true, yeah.
But see, this is the same thing that I don't get with the whole idea of when it looks at a picture, it's actually looking at a series of numbers. To the computer, it's not a 3D world. It's just more numbers. Right?
I see what you're getting at.
Like, you can't just put, it's not just like a person.
You're a
there.
philosopher.
It's not looking at pixels, though. I don't understand how a robot can possibly interact with a video game in a way that's not at the computer level of ones and zeros. Or numbers.
I think you're asking a very philosophical question. Suppose the robot actually had a computer screen in front of it and it used its camera to look at the
That's
computer
what they're doing?
screen.
So they're putting a camera?
Of course not. But that's what you should imagine.
Okay.
Or imagine that the world that the robot lives in actually looks like, Nintendo games. That's what it actually looks like. And, he uses his eyes, and those are the images that come in from reality. Just like the robot, we take those photons that come in through our eyes, they get imaged on a grid of neurons, and then, what we have as our input is a bunch of numbers, right? It's really continuous values. It's the amount of neurotransmitter that gets through that photoreceptor. So we're doing the same thing. It's computation. So the basic point is that, both systems must be doing computation. We have a number in there that represents the value of something, the number of photons that arrived at that pixel or something. But, we've always had these philosophical problems in feeling like we understand that, because to us, it really looks like we're seeing something out there, right? That's really there. And we know it's there. It really is there. But at the same time, how do you reconcile that with the fact that it's just a bunch of numbers in your retina? A couple of years ago, it was maybe the first time that someone trained a neural network to actually give super teenager performance on video games. So they had the Atari games, and they had trained using reinforcement learning. And the thing was better than humans on a third of the games or something.
Yeah, but how does that differ from when you would play a video game and you would say, do you want to play against another player, or do you want to play against the computer?
Oh, it's totally different.
Totally different.
Well, all right. But it's a very good point that you bring up, because it makes it seem like these things aren't all that intelligent. But the thing, what you have to understand is, when you play against the computer, it knows what it's going to do next. It knows what it's going to do. And when you have the deep network that just looks at the video and learns, it doesn't know what the system is going to do. It has to learn that. Unfortunately, a lot of those games, you could really know what the system's going to do. They didn't have a random number generator back in those days. Right. So they just had it was like the memory thing. If you remembered the sequence of the beats and stuff, you could actually just know.
Just do the math.
Anticipate the whole
thing.
It's like this. Completely deterministic.
Blip.
It's like blip. Wow. I kind of remember this.
So this is 1977.
Tomy. I remember that. I might have had this. Oh my god.
Mate, I think it's here, sir.
Oh, damn. Wait.
See, you only had 3 choices and you weren't able to predict it fast enough where it was going.
Oh,
see, but now look at this. See,
wait, I had this game. Did you go back in time and take this from me?
This is the best game of Blip I think that I've ever had. Oh, it's somehow it can be a little late. It has
you got me.
So
I was pretty sure it was going to go to 3 there.
Yeah, so this is a It says
analog computer.
Digital game, but it's completely analog.
Freaking wind-up game.
Yeah, you wind it up. It takes batteries, but the battery literally just lights the light. LED. Yeah. So that is analog. That represents analog. There's a certain amount of ambiguity.
Yeah. And there can be chaos.
And chaos.
Thanks to millions of teenagers over the years, right, we have all these video games that they're now training neural networks to play using reinforcement learning. That was one of the big things. At NIPS this year, many companies announced their package of interactive computer games for your nascent AIs to play.
AIs. To train AIs. To be the best AIs that they can be.
Yeah.
Wow.
Here's the way you would set up the test. You train the thing on a whole bunch of video games.
Yeah.
But what you test it on is a new video game that it's never played before.
But don't you want the video game to just represent the real world as closely as possible? Isn't that the idea, or no?
Yeah, eventually. We can't do everything overnight.
Yeah, right.
I mean, the things are going to slit our throats eventually, you know. So we got to take it easy. Don't get ahead of yourself here. Things are babies. We're trying to develop little baby AIs, you know, by training them on something that's simpler than the real world. Because if you want to train on the real world, we don't have a simulator. Right, you'd have to actually have robots, which is my plan to dominate the world. But everybody else, simulation, because it's easy, it's small, and you can actually learn something and show something. So if you could, you know, learn on Pac-Man and Donkey Kong and Dig Dug, and then play Centipede well, now you know you're onto something, right? Because it's different enough that it's not just learning the specific position of a number in the pixels.
Yeah.
Right. It has to learn to actually understand something about motion strategy. But the other key contribution of teenagers, besides coming up with these games to teach robots to kill us all, is that by playing those games originally when they came out, they were fueling the development of video cards. And video cards are actually one of the big computational infrastructures that allowed us to develop deep networks. Without the video cards, we couldn't have done it.
Come on.
Yeah. It's all driven by teenagers. If teenagers hadn't played video games, we wouldn't have big video cards with thousands of processors that can process all those pixels in parallel to render the graphics for video games. About 6-7 years ago that people started to take those video cards and say, hey, if you can compute images in parallel, we can do the opposite. We can do vision by processing the pixels that we see in parallel and do it fast. And so these things do things 100 times faster than a PC, which means that you can actually do an experiment that would have taken 2 years to run and find out whether or not it worked. You can do that in a week or two.
So it's literally like...
It's rendering.
It's utilizing the video card power in reverse.
Exactly.
Wow.
Literally, you would expect, like, okay, I'm going to have a model of the, like, 3D structure of the world, and I'm going to actually render that with lighting and all these things, right?
Yeah.
And that is something that's coming. People are starting to work on that kind of thing. But the predominant thing up to now has been doing these convolutional networks that are, it's kind of like location invariant recognition. And it's processing all of the pixels from the whole image in parallel to do recognition everywhere at once.
Yeah.
So, you know, when we said, oh, why did people do the deep hallucinations? It wasn't to make stupid images of dogs. It was trying to understand what's going on in the brain that we've created, this little perceptual piece of brain, right? The thing is, once you get into that analog domain, you can't program it. You can just expose it to data and see what happens.
Really?
And then you need to do like neuroscience to figure out what it's actually doing. This means that in the future, when you have robots running around that are learning using these kinds of models, you're going to have robot psychologists to understand how they're feeling, why they're doing what they're doing. When a robot crosses the line, then someone's going to have to investigate, what went wrong with these robots. Why did they learn what they learned?
I think that was an episode of Westworld.
Yeah, that it was. This happened in reality, right? Microsoft had this chatbot that they trained on chat rooms. And the classic garbage in, garbage out, the thing learned to be like a racist chatbot.
Didn't it turn into a Nazi or...
It was offensive. Whatever.
It was just a general white supremacist.
It was a troll.
It became a troll.
Yeah. It learned to be a troll.
Yeah.
Because, trolls outnumber us.
But we don't realize it because we're not focusing on that. But this thing did focus on it.
Exactly.
And it spit it back out.
Again, it's filtering, it's... The things cannot modulate. They can't modulate themselves. They're not polite. They're rude.
Right.
And
as we've seen,
you train them on trollage, and they learn trollage. So now that's why this, game console thing is really significant. Because if this is what the new AIs are training on, virtual reality composed of games where you shoot things that are alive and make them dead as the main goal of existence.
That's not good.
It could be bad. Yeah, that could be bad. But my army of little toy robots that goes around and just learns how to entertain kids could be good. So there should be some sort of, academic pact to only expose nascent AIs to human-friendly games.
Are you saying that in jest, or are you saying that seriously?
No, seriously, I think there should be that. I do.
Really?
I'm saying it because it's also funny. And weird, but it's the truth. The truth is funny.
Let's get into this WaveNet.
WaveNet
is a deep generative model of raw audio waveforms able to generate speech which mimics human voice and sounds more natural than the best text-to-speech systems.
It's incredible. I would describe it as accomplishing maybe 2 decades of incremental improvements in speech synthesis overnight.
But what does this have to do with intelligence, though?
I think we overestimate our sort of logical intelligence. That was the classical AI. But perceptual intelligence is really important and really difficult. About a third of your brain is doing vision.
No, but this is
the amount doing chess playing is a tiny fraction.
But this is different than neural networks and artificial intelligence. Now we're just talking about replicating the human voice, right?
Yeah. It's important to separate the task from the method. The task is to replicate human voice, but the method is important here because that's what made it finally sound real. So after all these years.
Here's we can play some of it here.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. Aspects of the sublime in English poetry and painting, 1770 to 1850.
It still sounds a little fake.
I agree. But you know what? That one that you just played, that one is fed a stream of conventional speech synthesis parameters. So it can do better.
Oh, I see. It can't do better.
You got to play the spontaneous one.
That's what I love, too. The one where they didn't tell it what to say, but they just had it say something. So the result is that you get this almost like it's speaking in tongues. It's very creepy. So here's the first one.
Sådan. It was fantastic. Jeg still ser man, but the next thing I sit out of teacher did the thing that got kid so I'm plus.
So to me, that sounds much more realistic, even though it's gibberish. But the voice quality sounds more physical and real to me. And I think it's because they didn't feed it a bunch of old school speech synthesis parameters.
It sounds like a real language you don't know. Spoken by a real person.
I mean, most important thing is that it sounds like, a real physical system.
Just even. That was this. There's lots of advocating if you challenge. But the name could I Jeff over. It's over to you to be the not day. That here with him.
It's so creepy.
Physics is hard to simulate.
So creepy.
Can you imagine simulating the actual mouth shape and tongue position, vocal cords, millisecond by millisecond, simulating the full 3D reality and the acoustic wave propagation? I mean, it would take a massive supercomputer weeks to compute just a second of that. So even though this is actually also really slow, maybe 80 times real time or something, it's amazingly fast compared to what it has to simulate, like reality. It's simulating something that has billions and billions of,
Yeah, I like how somehow breathing sounds were incorporated.
Foundry and Eckhart.
There's one of these that's...
Do you remember the share about study given as well?
vocal fry.
But it's going to be Tao Seki.
They all kind of sound Gaelic.
Should have just tagged pictures in.
That's got the big breath in it right there. That creeps me out.
Should have just tagged pictures in. Tao.
That's so creepy.
Yeah.
Exactly.
It's creepy.
A lot of breathing in that
Because you
one.
never heard that synthesized.
Yeah.
It's actually surprisingly hard to do that. And the reason is all these neural networks, they're trying to predict something, right? And if you just naively train a function to predict something, you're doing what in statistics is called regression, right? You'd have a bunch of things that come in, you try to predict something by combining them, and then you get a prediction. And that prediction is like the average value of the thing that you're trying to predict, given all the inputs. It's the average value. They called it regression because it inevitably went to the middle of the distribution of possible values. And because it goes to the middle, it smooths everything out. And so all the neural network stuff completely failed at generating things until this most recent stuff. They're doing something very different from regression. To appreciate that stuff, you have to realize that every single bit of the output is completely generated by the deep network. It's not concatenating together little snippets of audio that it remembers. I mean, of course, we don't know what it's really doing. It may, in effect, be doing that. But at least on the surface, you'd say, you put in some numbers, there's some nonlinear functions, and out comes some other numbers. That system is just generating that stuff only by virtue of having been trained on it.
So now that we have this model, does this make it easier to interpolate actual human speech? You know what I mean? I'm like,
it's brilliant.
Is that how that works? Like
no one. This came out a couple of months ago. But that's how fast things move now. So now this is going to be the old way of doing things in another month or two. But you're right. Obviously, that was the first thought that we had, since I and my team, we work on enhancement and cleaning up, separating signals. So we thought of applying it to that, because if you have some speech and then there's a noise right in the middle of it, that noise is gonna mask out. I'm trying to mask my own speech. It's gonna mask out part of the speech, and we don't hear that, right?
Right.
The human perceptual system is able to sort of like cover that gap, unless the thing that's masking out is other speech. Then it becomes really hard to follow one or the other. But that's exactly the goal. It's to synthesize the speech that's missing in between.
And that's all done just by pulling out the numbers. Like when it gets down to the most basic, essential elements of it, it's still patterns of numbers, right? And
I think there's something that makes it even harder to understand, which is that we're talking about like a system that you could think of as a continuous analog thing, like a Moog synthesizer, right? But it's implemented in digital, right? We're going to simulate those numbers and how they move from one number to the next. Floating point number is a set of bits, right? Even though it represents continuous numbers, it's just a set of bits. So there's layers of computation here. At the bottom, we actually have a symbolic computer, and we're using to simulate a continuous one. The most exciting thing is that we're trying to train those continuous things to do the symbolic things at the top.
Yeah.
So it's like a symbolic sandwich with the continuous stuff in the middle. Kind of like a whoopie pie of computation.
So I hope you're following this, everybody.
Here's a challenge for you. How about synthesizing speech with different emotions?
Makes complete sense.
Yeah, it's very challenging. But I've always thought that's music, right? That's what you hear when you hear a guitar solo, that when bending the notes, it's trying to evoke that prosody effect of speech, right? Which emphasizes emotions.
Will there be a time where we can just run a guitar solo through an application And it'll
I
just
see
tell
what you mean.
us, it'll just spit out a poem of the guitar solo.
Right. And it'll be just only emotion words. It'll be like, oh yeah. And then it'll be like, God damn you. And then it'll be like, yeah, that's good again.
Are you working on that? The speaking back part? Or are you just working on the recognition part?
So synthesis is obviously just generating something. But what we want to do is alter the perception. Like, so you listen to a combination of sounds, and you will have to generate each of the component sounds. Now, part of those things are observed. When the sounds that you're generating are really loud, right, then you can just copy them from the input to the output. But when they're quiet and another sound is louder, you have to fill in the gaps. You know, filling in is something that the brain does really well, right? Most people know that there's a spot in your retina that can't see, right? It's like a little blind spot.
Yeah.
But we can never really see the blind spot because we have two eyes and the blind spots are in different places. And you have to really focus. Basically, human perception is about filling in. You think about you're moving your eyes around. The world looks like it's steady and it's always there and in one place, but your eyes are going from one place to the other, just picking up little bits of information.
So that's where the idea of predictivity, the importance of predicting what's going to come next.
Yeah, we use that to fill in the gaps. We have a project doing audiovisual question answering. So the idea is you have movies that, for the sake of blind people, have been provided with an audio track that describes what's going on in the scene.
Yeah.
So now you have, I think there are about 600 movies. So right now there's about 1,200 hours of video with descriptions of what's going on. This is a good amount of data, and you can train a network, feeding in the video pixels, having it encode. The network is going to process those video pixels, and then you have the description of what's going on. So then it tries to predict the words in the description.
Now we're getting into the same territory that I don't understand. The language, now you've got to have a language processor to interpret what a sentence means, what words mean.
Well, all you're trying to do is select the next word. And the same is true of the computer. The computer is just trying to select the next word. It has a list of words.
Yeah.
Let's say there's, 500,000 possible words in English language with conjugations and plural, singular, all that stuff. You got a big, giant list of words. You just want to select a good next word. So it has a representation in there of the probability for each of those words. You got 500,000, 500,000 words, and we're just going to estimate the probability that that next word should be the next word, given all of the words that you've seen before and all the video you've seen. And so it just goes down one word at a time and tries to estimate the probability, and then we choose like maybe the most probable word, or we sample according to the probabilities of the words. That's what WaveNet does, right? The words in WaveNet are the individual values of amplitude for a given sample. Just carve that up into 256 possible values, and we get a probability for each of those values, just for one sample, like how far above or below zero it is. And we just decide on a value. And given that value, we feed it back in, and we try to pick the next value. We assume that we have the words. Now, each word is converted into just like a number. It's word number, 365,422. Right?
Yeah.
That's the word. And then the next word is some other number. But the system is going to learn to map those individual like indices into some pattern of activity. Or you could even just start with the patterns. Like there's many methods of learning a pattern of numbers that should correspond to each word, so that words that have similar meanings are close together, and words that mean different things are far apart. If you look up the word to vec stuff from Google, the simplest model ever, but amazingly effective at providing this like vector associated with each word, such that things that mean similar things are in the same direction. Okay, so you feed those vectors in one at a time, and they're transformed into some kind of internal state representation, which is continuous. And then you have connections between the previous word and the next word, and the next word, and you have multiple layers with connections across. So once you've digested those words, you can think about producing the next word.
And that's the goal. Predict the next word.
We're working on, can we make use of this really rich data that has video and descriptions of what's going on to try to get better representations of meaning, semantic representation. So from the video, we want to get a semantic representation. And from the text, we would like to have semantic representations of text. Prior to this kind of data, people only use the fact that words are close to each other in text. So it's kind of like an assumption that if two words are close together in text, their meanings are more similar. It's kind of bizarre, right? You wouldn't really think that should be true, but if you train on very large amounts of text, you do get good representations that have that property. But now, like when you have video, which has an actual image of a car and a dog, and then you have text that actually mentions the car and the dog, now you can start to associate a real physical representation with that word dog and word car. You know what they look like. You could generate a picture of a dog. Or when you see the dog, you can recognize it as a dog. And this way, obviously you could train a system to recognize dogs and cars, but the thing is, the number of objects in the world is millions. It's almost unbounded. It's not the number of words in the vocabulary, it's much more than that, right?
Yeah.
Because if you think about something like a lightsaber.
Yeah.
Just 2 words, right? But that's a very specific thing. So to be able to recognize that, you need to be able to combine concepts together and then have examples and recognize something like that. So it's a very, very wide space of possible things in the world. And so the only way we can get at that is using massive amounts of data. And so this task, we think, predicting text from video and sort of understanding video by virtue of the labels that are in the text is opening up to much broader category of things that we can understand.
What is really important in terms of human consciousness, and it's simply the idea that we've labeled things and that we're able to communicate what those labels are. Whether it's verbs or nouns or anything. Everything is just a label for something else.
Speech is magic, right? I mean, how is it possible that I can just sort of wag my mouth and, something...
You're vibrating the little muscles in your... voice box there.
Yeah, I gotta move my tongue around.
And then you're moving your tongue around.
And then these invisible vibrations go from me to you, and then you get an idea in your head that has something to do with what I said.
Vibrates the bones in my ear.
Yeah, bones.
And that gets interpreted.
Actually, bones. A series of bones connected what I said to what you thought.
It's like the blip game. It's mechanical.
Yeah. Powerful stuff. No, I mean, the world is a big computer, if you think of it, and the amount of computation that it does is vastly more than any kind of computer that we can actually harness. So what we're aiming to simulate is something that is, daunting. So we should really pat ourselves on the back whenever we achieve anything, because a real brain, it's a system with 100 billion neurons and thousands of connections. I mean, it's a really big, impossible to simulate thing. Quantum computing, if it can be realized on a large scale, would change everything, right? Because the amount of computation that could be done for certain problems is just vastly more than what we can do with conventional computing. And it's a matter of what's known as computational complexity. So you try to quantify how the amount of computing increases as the size of the problem increases. If you have to find the shortest route between a bunch of locations, how does the problem of finding the shortest route take more and more time as the number of locations goes up? Right? That's the computational complexity. And quantum computers can have computational complexity that's only linear in the number of elements, as opposed to exponential. So they can take a problem that's hard and make it easy. I mean, this is all driven by the data, and kind of part of the mind share right now in machine learning, and a lot of the big heavy hitters at NIPS were talking about this, is that unsupervised learning can be more powerful than supervised learning. So to understand what I just said, you have to understand what supervised learning and unsupervised learning are. Supervised learning, you have like a label for every example. Like you have an image and somebody said, oh, that's a dog. And you have another image and somebody said, oh, that's a car, right? And so you have a whole bunch of images with labels and you're trying to just predict which category that image is in. That's sort of simplistic, classical supervised learning. Unsupervised learning can be more subtle. It's like you have a bunch of images and now the task could be, let's try to predict one half of the image given the other half. Or let's try to come up with categories on our own for what are in all those images without anybody telling you this is a car, this is a dog. Why don't you figure out what the classes are? That paradigm is more difficult, and it's been challenging to do that with deep networks, but it's ultimately more powerful because if you think about it, you could have a set of images and a set of labels, and then you have one label per image. But if every pixel in that image is also kind of a label for all the other pixels, then you have many, many problems that you can learn from in one image. I'm paraphrasing here a little bit from Jan LeCun's keynote speech at NIPS, where he talked about that kind of stuff. But it's something that I've felt for a long time, that unsupervised learning ultimately is very powerful because it allows us to use the data that we have.
Do you think that mimics more closely how we learn as babies? And we're just exposed to everything with no explanation, and then we just have to formulate a system to understand the world.
Absolutely. I mean, as babies, it's mostly unsupervised learning. You have to understand what good and bad mean before you can use that as your signal for whether you did something good or did something
My
bad.
kids still don't know.
Exactly.
Yeah.
Unless it's food. Sugar is good. Everything else is bad. I think the brain is a self-organizing system. Self-organizing is kind of an unsupervised concept.
Given all that's happening, to make a prediction, at what point do you think we'll actually be able to hold intelligent conversations with robots?
So at what point will we be able to hold intelligent conversations with humans? That's my question. No. That's the definition of intelligence.
Yes.
Humans. No, but I mean, right. Pretty much. But the answer to that question is people are coming up with things that are almost intelligent-ish now. And so it seems to me it's a matter of scaling up and the amount that's learned, but it'll be soon. The amount of data that's available to train systems on has been growing sort of exponentially because of the internet and things becoming available. It used to be the case that only big industry labs that had a server that was, running some actual application would be able to collect enough data to really train a big system. Say speech recognition system, you need a server that's collecting data from call centers over the phone, and then you have a lot of data to train on. But now, because of two things, we have a lot of data. One thing is that the internet makes the data available. The other thing is that we're using better unsupervised machine learning algorithms. So we're doing this kind of learning that doesn't require human labels. So the data is just there. We can train the video on the audio and train the audio on the video, things like that.
So it sounds like we're just really on the verge of having robot overlords.
Maybe underlords. It's not clear. It's like your kids, depending on how you raise them, they'll turn out to be different kinds of people.
Let's look at some of the deep clustering that you've done.
So the idea here is that a robot that's out in the world is going to have to understand what's going on around it. And separation of one sound from another is sort of essential if you want to recognize the sounds. So now imagine the worst case scenario for recognizing speech in the context of some other interference is if the interference is actually other speech. And it might even be the same gender or even the same, almost the same type of voice. And then it becomes really difficult. How do we do this? But this is the legendary sort of cocktail party problem that started the field of cognitive science. Back in the olden days, there was a lot of interest in selective attention as a basic perceptual process, and the auditory domain was like a good place to look into that because sounds overlap, right? They just merge together. So the goal of this was to develop a system that can actually do what humans can do in the sense of attending to a single source, a single voice in a mixture of speakers and understand what's being said.
Okay, so let's listen to this source data. So this is two actual women talking, recorded at once?
I would go with the sample down
the first
there.
one? Okay.
July delivery platinum surged $13.10 before settling at $622.90 an ounce, up $12, period.
They're reading from the Wall Street Journal there, just random sentences.
And so now if I try, I could actually focus on one or the other of those voices.
Yeah. Try it.
July delivery platinum surged $13.10 before settling at $622.90 an ounce, up $12, period.
One voice is louder, so it's hard, but I can sort of do it.
People can do this. Yeah. Two speakers, and the thing is, it's been a complete disaster for automatic speech recognition up until now. Computers have not been able to do this, and this is maybe the first time that on a practical level, you could actually do this.
Here's one of the speakers being isolated completely artificially.
Yes.
The mid-July increase came even though automakers are offering incentives on fewer cars this year than they did last year or earlier this year.
And that was the quieter voice, right?
July delivery.
Yeah, that was the quieter voice. And here's that louder first voice.
July delivery platinum surged $13.10 before settling at $622.90 an ounce, up $12, period.
Wow. I'll provide a link for this in the description of the podcast, but this is at MERL.com. If you just search for MERL deep clustering, I think this will come up. And so the ultimate goal is what? It's just to facilitate better comprehension.
The ultimate
overall
goal would be to actually be able to understand what's going on in your environment. You may have some background noise, maybe the baby's crying and there's a dishwasher going and you're listening to some music and you're following, the drums and you're following the voice, and now somebody speaks to you and you need to recognize what's being said. So it's sort of normal for audio perception to have to filter out different sources and pay attention to one or the other at different times. So this would be a sort of an enabling technology for any kind of agent out in the world that can hear.
So how much of this already exists? Because I've noticed, on my iPhone, that when I'm giving a location to Apple Maps or Google Maps or whatever, and the radio's on, it's still pretty good.
It's still pretty good, yeah. I mean, and this is a recent development that it's pretty good. The techniques they're using are similar to what we're doing. There are two differences. One is that they use multiple microphones and they do kind of directional selection. We're not doing that. Here, our problem is harder. We're starting with just a single microphone recording.
But the fact that it's able to isolate my voice against other voices already in the iPhone, how it's doing it in real time.
Right. It's probably using directional microphones to do that. Here, with a single microphone, imagine the problem with two speakers, both of which are female, or both of which are male, and trying to separate those. Now, you don't have direction to help you, and you can't use the fact that there's one type of sound versus a different type of sound. So separating your voice from the engine noise and the road noise in the car is in some sense easier because we can have data that really is just two different classes classify whether it should be voice or engine noise. But here it's the same type of noise, so you can't be separating based on the type. You have to be tracking and following the evolution of each voice. So we can actually do this even when it's the same speaker's voice mixed together.
Wow.
But they're saying different things at different times, so it's following the continuity pattern, which is a problem that is inevitable even if you have multiple microphones, because two sources of sound could be in the same direction, and then you don't have any benefit for having multiple microphones.
So is any of what we just heard an artificial voice that's recreated and that's created based on the prediction of what sound is going to come next? Or is that all literally the separation of two sounds?
So part of it is separation and part of it is filling in. So the initial thing that we do is we analyze the sound into what's called a spectrogram. So at each time you have the energy that's in different frequencies. And if you can identify which frequencies at a given time are dominated by one speaker's voice versus the other, and you just select those and set the other ones, the ones dominated by the other speaker, to 0, then you can reconstruct a signal that sounds pretty good.
Yeah.
But you've got zeros in it where the other speaker was talking, and that basically puts holes in the signal.
Yeah.
And that screws up speech recognition, and eventually if you have enough speakers mixed together, it makes it harder to understand. Right. So then our next step is to fill in those holes by interpolating. Given the part that we were able to observe, that where this voice dominated, we try to interpolate and anticipate the parts that are missing, that we cannot observe. The interesting thing is that the way we do this is independent of the number of sources. Using the same representation, we solve the problem of different numbers of sources. If two speakers are mixed together, we train a network, and then we can infer when three speakers are mixed together, we can get three sources of them.
So a crowd of people.
Ultimately, it could be a crowd of people and other noises. That's where we're going, to scale this up to many different sources. So what we do is we train the network to produce a different vector for each time and frequency combination.
Yeah.
And that vector, just like how we were saying with words, we represent the meaning with a vector of numbers. Now we're representing each part of the spectrogram with a different vector of numbers. And we're training the network so that if two different times or frequencies come from the same source, those vectors should be more similar. And if they come from different sources, they should be further away from each other. So once we train the network to interpret the spectrogram that way and sort of paint it with this set of vectors, then we can cluster the vectors and separate the sources.
And this is the way that the government...
The robot government.
The robot overlords. That's what I meant. This is how the robot overlords will ultimately be able to listen in on everything that we say, no matter how big the crowd that we're in. They will just isolate our conversation.
But they won't be in competition with us, really. As long as we provide them electricity, they'll be fine.
Right.
They don't really care. They can use us for entertainment.
Because it all has implications in everyday usage.
That's right. Every company is going to be learning from everything that you do from now on.
So good luck to us all. Well, John, thanks so much for coming by.
Thanks for having me.
It was really fun. And being a part of this episode of Device Squad, the podcast for the mobile enterprise from Propelics. Bye-bye, everybody. I'll see you next time. So, dude, there's like a one-player mode on that thing. You can play the blip. Check it out. I don't know. I'm not sure how that works, but just turn it.
It's completely mechanical, so how does it decide when to hit the ball?
See that? It's kicking your ass. Look at that.
It never fails.
You can't fail. Oh.
But if you could train a robot to do well at this point, even given how stupid it is, it would still be the most amazing robot.
Yeah, nobody's putting an AI in this thing to figure out how to get 1, 2, or 3. You want a beer?
Yeah, there's one more. I mean, it's Wednesday, right?